Welcome to today's Explainer. Today, we're demystifying the immense hardware and software that it takes to actually run high-density AI factories. If you follow the AI space, you already know NVIDIA's Blackwell architecture is an absolute powerhouse. But deploying these multi-million-dollar chips isn't just about plugging them into a wall. It requires a wildly sophisticated orchestration of physical infrastructure and software management. So today, we're taking a magnifying glass to Supermicro's SuperCloud Composer to see exactly how these highly expensive, mission-critical data centers are operated in the real world. To truly wrap your head around the thermal challenge of NVIDIA's Blackwell B200 platforms, just listen to this massive figure. 250 kilowatts. That is the cooling capacity required from a single 4U coolant distribution unit. I mean, that is just a staggering amount of thermal energy. We are way past the days of just blowing cold air across a server board. To keep these heavy-lifting AI workloads running efficiently without, literally melting themselves down, data center engineering has had to completely evolve. Okay, here's our roadmap for today. First, the Blackwell AI factory. Second, visualizing with PodView. Third, inside the compute node. Fourth, monitoring GPU performance. And fifth, power and leak enforcement. Let's dive right into Section 1, the Blackwell AI factory. Think of the Coolant Distribution Unit, or CDU, as the data center's circulatory system. It basically pumps this precisely calculated mixture of glycol and water directly across the cold plates sitting right on top of those incredibly hot CPUs and GPUs. When a massive AI model starts training, this liquid loop is absolutely the only thing standing between your massive capital investment and a literal over-temperature meltdown. And this brilliantly illustrates why liquid cooling isn't just a luxury anymore. It's a strict necessity. Just look at this comparison. You'd need a bulky 10U system, complete with a redesigned chassis for extra thermal headroom, just to air-cool the B200. Contrast that with packing the exact same compute power into a sleek 4U liquid-cooled system using cold plates and advanced tubing. It's a monumental saving of floor space, which, as we know, costs a fortune in a modern data center. Now, this space saving translates directly into massive scale. Supermicro actually uses a patented vertical coolant distribution manifold that doesn't eat up valuable rack space. Because of this clever design, in a 52U rack, you can pack a staggering 96 Blackwell GPUs. Scale that out using NVIDIA's InfiniBand networking, and you can build a non-blocking supercluster of 768 GPUs across just 9 racks. That means zero data bottlenecks slowing down your operations. Pretty incredible, right? Moving on to Section 2, visualizing with PodView. Because, let's be real, building all this physical hardware means absolutely nothing if your software is blind to it. In SuperCloud Composer's PodView, an admin conducting day zero setup follows a very logical sequence to create a digital layout. First, you create your rack configuration. Then you plug in the PDU, add your liquid cooling CDU manually, and finally, you command the software to discover your shiny new servers. It does this using SSDP or an IP ping spray, which is basically like sending out a digital sonar ping across the network to find your exact hardware and map out the data center automatically. Which brings us to Section 3, inside the compute node. Now that our floor plan is completely mapped, we can zoom in past the rock level directly into a single 4U compute node for day one operations. The really crucial point here is the sheer breadth of metadata pulled using Redfish, which is the industry standard for remote hardware management. The DevOps admin isn't flying blind here. From a single pane of glass, they can see the system uses Intel CPUs, with 96 cores spread across 2 NUMA regions. This is essentially how the processors organize and share memory efficiently. They can monitor all 8 local B200 accelerators and even check out out-of-band and NVMe drive health. If a drive starts failing, they just click a button to flash a physical light on that exact drive so a technician on the floor knows exactly where to go. Let's look at Section 4, monitoring GPU performance. Going into day 2 operations, if you want to squeeze every last ounce of performance out of an AI model, you absolutely need high-fidelity telemetry. SuperCloud Composer acts as the central nervous system here, backed by Prometheus-based API integration and Grafana-style dashboards. And what makes this so incredibly powerful is the granular polling interval. It actively queries the hardware every 10 seconds. When you're pushing this much electricity, heat builds up almost instantly. So tracking that unit power draw and those individual GPU temperatures historically ensures you aren't accidentally pushing the hardware past its thermal limits. Finally, Section 5, power and leak enforcement. So what happens if a coolant leak is detected? Honestly, this is the absolute most terrifying question for any facility manager. You've got hundreds of gallons of liquid pumping directly over millions of dollars of sensitive electronics. If external sensors detect a liquid leak dropping inside the rack, you just can't rely on a human to manually click shut down in time. Monitoring means nothing without automated reflexes. So administrators can define some incredibly strict enforcement rules. Take a graceful shutdown. You might wonder, why on earth would you delay shutting off power during a leak? Well, if that system is a liquid-cooled storage server holding your primary AI training dataset, an immediate hard kill could corrupt vital files. A graceful shutdown delays the power off by a few minutes, just enough time to close those files safely. But for pure compute nodes, you'd likely configure an immediate, instant shutdown to protect the silicon the very second a drop of liquid is sensed. And this brings us to the ultimate failsafe. Utilizing universal agents, the software maps every single server to a specific electrical outlet on an integrated Schneider electric PDU. If the CDU detects an inconsistent temperature ratio or a flow rate issue, which basically indicates a severe anomaly in that closed loop, the software bypasses the server entirely. It triggers the PDU to cut electrical power directly at the mapped outlet. It can even instantly kill power to the entire rack in a fraction of a second to prevent a catastrophic short circuit. It's a total lifesaver. So, I'll leave you all with this final thought. Building the physical AI factory, the advanced cold plates, the sleek 4U nodes, the massive vertical coolant manifolds, is an undeniable engineering marvel. But as AI chips grow ever more power-hungry and thermal tolerances get tighter, hardware alone is incredibly vulnerable. Without an intelligent, automated software nervous system to govern it all, true sustainability, efficiency, and safety will just remain out of reach. Is software actually the real secret to the future of hardware? Thanks for joining us on today's Explainer, and keep exploring.